Now that we know how to solve systems of linear equations using Gaussian elimination, we want to look at the idea that there are really three possible outcomes as far as the solution set to a system goes. There are three cases. One, we could have a system with no solutions or zero solutions. We could have a system with just one solution, or we could have one with infinitely many solutions. And with these three examples, these are in 2 dimensions, so we'll actually be able to visualize them quite well and see why it is that they have 0, 1, or infinitely many solutions. And we'll also be able to look at the reduced matrix and immediately identify which of these three cases we're dealing with. So in this first case, we have x plus y equals 1 and x plus y equals 0. Now, if you think about the logic of what this system is saying, it's saying that there are two values that when I add them together, I get 1. And the second equation seems to emphasize that those same two values that I add together, x and y, I get 0. So I can't think of two values that I can add together and get 1 and also 0. In fact, if we plotted this system here, what we would see is that one of them has a y-intercept of 1 and then crosses the x-axis at the point 1, 0. And this second one here, x plus y equals 0, is actually, well, this one here is the line y equals negative x plus 1. And that's this equation here. And then in the second equation, this will be y equals negative x, and so that one will look like this, y equals negative x. Now you can see that they both have the same slope, and since they have the same slope, but different vertical intercepts, they are parallel and will never intersect. So already I can say that this system is going to have 0 solutions. Now, keeping just to the elimination process, if I set up the matrix for this, the coefficients of x and y are both 1. So my augmented matrix will be 1, 1, 1. And in the second equation, we'll have 1, 1, 0. Okay, so if I perform the elimination process, I think what I'll do first is I'll take negative 1 times the first row and add it to the second row so that I could cancel out this guy here. So I'll take negative 1 times row 1 and I will add it to row 2. I'll put the result in row 2. So this is indicating that I'm only going to change row 2. So row 1 is going to stay the same. I'm not doing anything there. I'm just using it as sort of a pivot to allow me to cancel out values in the second row. So if I take negative 1 times these values here in the first row, negative 1 times 1 is negative 1, plus 1 is 0. Negative 1 times 1 is negative 1, plus 1 is 0. Negative 1 times positive 1 is negative 1, plus 0 is negative 1. Now at this point you might see a problem, and that is our next step would be to use they're already all 1s, so I don't have to worry about scaling the rows at all. So I didn't have to scale the first row by anything since there was already a 1 in the x coefficient position. Normally what I would do now is I would get this to become a 1, but notice that it got canceled out, that I have a 0 here. There's nothing I can multiply 0 by to get 1, and therefore, since I can't have any other value other than 0 here, I'm not going to be able to multiply this row by any constant and add it to the first row to cancel out this positive 1 there. So we've effectively run out of things that we can do. Let's take a moment and unpack what these two equations are now saying. This first one, these are the coefficients of x and y. The first equation says 1x plus 1y equals 1. So that first equation didn't change in any way, shape, or form. The second equation says 0x plus 0y equals negative 1. Now keep in mind that this system we know has 0 solutions based upon the graph. And this second equation actually, the left-hand side is equal to 0, since 0 times anything plus 0 times anything is 0, and we get 0 equals -1. Well, unless we believe that we've just proven that 0 and -1 are the same number, this right here is a false statement. And so what that means is that our system has no solution. If we ever get a false statement in mathematics, that means, well, we either made a mistake or the system is not consistent. So this system has no solutions, and we say that it is inconsistent. That's just another word for no solutions. Okay, so if we end up with a statement of the form 0 equals a non-zero constant, and actually one of the things you can do here is multiply both sides by -1. So if you did this with a calculator, you would actually end up with the statement 0 equals 1, but we didn't go any further because we know that no matter what we scale this row by, it'll still be 0 equals some constant, which will be a false statement in general. Okay, so that's our 0 solutions case. So we're going to end up with a false statement, and that's really key here. That's how we will know that a system has no solutions. Now in this second system, we have the line, if we were to get this into slope-intercept form, y equals -x plus 1. And the second equation, if we first of all divide both sides by 2, then this is actually x plus y equals 1, which means the second equation actually would reduce to y equals -x plus 1 as well. Now if we plot these two lines and ask ourselves, what points do they share in common? Well, there is y equals -x plus 1. And if I also plot the second equation, which is the exact same equation, then we can see that there are infinitely many, I'll write it like that, intersection points. Right? They're the same line, so they share every single point in common. So they share that point in common, and that point, and that point, and that point, and all the points in between, and all the points that these lines will traverse as they go from -infinity to +infinity. Okay, so now the question is, how does the elimination process lead us to this conclusion? So let's see what happens when we set up our augmented matrix. So the first row will be 1, 1, 1. Coefficient of x, coefficient of y, constant. And the second equation will be 2, 2, 2. So what I think I'll go ahead and do is I'll take -2 times row 1, and I will add it to row 2. Okay, so that result is only going to change row 2. So if I take -2 times the first row, and add it to the second row, -2 times 1 plus 2 is 0. -2 times 1 plus 2 is 0. -2 times 1 plus 2 is 0. And now you can see here that we ended up with a row that results entirely in zeros. Now that by itself is not a problem, because this line says 0x plus 0y equals 0, which reduces to the statement 0 equals 0, and that's true. That's always a true statement. We didn't end up with a false statement like we did over here. Unfortunately, there's nothing else that I can do because I can't pivot off of the second row to allow me to cancel out the 1 in the first row. Because again, I can't multiply by 0 by any quantity in order to add it to 1 and get 0. So this system is done, and this is the best that I can do. So the first equation really just reads x plus y equals 1. And what this means is that any two numbers that add to give 1 are solutions. In other words, if I look at it this way, if I say, well, x plus y equals 1, then I can say y equals negative x plus 1. Okay, that's just solving for y in that equation. In other words, there are infinitely many choices for x and y here, but the reason I solved for y is because now if you give me a value of x, like if x is 0, 0 plus 1 is 1, and you can see that 0 plus 1 is indeed equal to 1. If I plug in 1 for x, negative 1 plus 1 is 0, and 1 plus 0 is 1. If I plug in negative 5 for x, negative 5 is positive 5, plus 1 is 6, and you can see that negative 5 plus 6 is indeed equal to 1. So that this list goes on, and I'll never run out of points. I can even use decimals in here, like let's say 0.2. If x is 0.2, then y will be 0.8, and 0.2 plus 0.8 is indeed 1. So here we have infinitely many solutions. And how do we know that? Well, there are two things. First of all, there are no false statements. And secondly, and this is the case in general, there will be at least one row with more than one non-zero coefficient. And this, of course, is after the reduction process. So here we saw that we didn't end up with a false statement, and we ended up with the first row containing more than one non-zero coefficient. So the coefficients are 1 and 1. Once the elimination process has terminated, because we can't do anything else, and because we end up with 1, 2 non-zero coefficients, that in conjunction with the no false statements outcome allows us to guarantee that there are going to be infinitely many solutions. Now, we're only looking at two equations and two variables. The reason I say there will be at least one row with more than one non-zero coefficient is if you had three equations, you could actually end up with two of those equations, two of those rows ending up with more than one non-zero coefficient. Now, finally, in this third case, here I have x plus y equals 1, which is still the equation y equals negative x plus 1. And in this second equation is really just the statement y equals 1. So if I graph these two equations, and I'll try to be as precise as possible here. Here is the line. As I say, I'm trying to be precise. It's not very precise. But y equals negative x plus 1. And then I plot the line y equals 1, which we know to be a horizontal line that goes through y equals 1 and has a slope of 0. So there's the line y equals 1. And I see that they intersect right there, just at one point. They have different slopes. And this is the point 0, 1, from what I can infer from the graph. Now, we already know how this is going to pan out because we've already established a process for systems with exactly one solution. So my first equation will be 1, 1, 1, and it's augmented matrix. Again, coefficient of x, coefficient of y, constant. And the second one says 0, 1, 1. Now I already have a 1 here. I have a 0 here. I have a 1 here. And now I want to cancel this 1 out and make it a 0. So that means I'm going to have to take negative 1 times row 2, add it to row 1, record the result in row 1. So I'm going to leave row 2 the same. I'm not changing anything there. And then in the first row, I'm going to take negative 2 times 0 plus 1, just 1. And again, this is why we work kind of in this order. Make this a 1, get that into a 0, get this into a 1, and then make this final value into a 0. If we go in that order, we won't undo the work that we've already done. So negative 2 times 0 plus 1 leaves this value unchanged. Negative 2 times, this should be negative 1. Negative 1 times 1 plus 1 is 0, as desired. Negative 1 times 1 is negative 1, plus 1 is 0. So now we can see we have a 1, 0, 1, 0. And now we can interpret what these equations are after this elimination process. So the first row says 1x plus 0y equals 0. The second equation says 0x plus 1y equals 1. This first statement really just means x equals 0. The second statement means y equals 1. And so our solution set is x, y equals the point 0, 1, which is the same thing we found by looking at the graph. So these are the only 3 possible outcomes, and what we're really going to want to focus on is how do we represent a system with infinitely many solutions? How do we describe the solution? We kind of did it here. We just said that any ordered pair that satisfies y equals negative x plus 1 is a solution, and we could list some of them. But what's the best way to represent the set of the infinitely many solutions? This is just sort of one way, but there's a better way, and we'll see how to do that in another video within this lesson.